age could be a risk factor for development of asthma in the child, but it's not an immediate intermediate pathway between use of hair dye and asthma. So age does seem to meet the definition of confounding. So the first question on the lab basically asks you to draw the diagram, demonstrating how this would look. So here's the answer. So hair dye is the exposure, and we're saying that it's possible that, what we're looking at, we think that that hair dye could cause pediatric asthma. And so that's the main risk factor and the main disease. But we're also concerned that maternal age could actually be a confounder here. So you see that maternal age could actually cause or be causally related to pediatric asthma. But maternal hair dye or use of the hair dye is not going to cause someone to just age. It just is associated with the confounder, but it doesn't cause it. So this is how it would kind of look. So that's the first question, pretty basic. I'm not going to really ask you to draw diagrams anywhere, but you see them on the slides just to sort of help you.
Professor?
Yes?
Could you put maternal age as the exposure, and then maternal hair dye could be like a modifier, right?
Yeah, you could. It could work that way if you have a hypothesis, and it meets the definition, you could. Yeah, I mean, sometimes that's what happens here, So now let's open SPSS, and let's actually do the stratified analysis together so you can see how this works. And I think, and I hope that I did do Breslow Day in this. I did, good. Okay, so you can see how the Breslow Day thing works too. So the next question number 2 says, knowing that confounding and mediation look exactly the same in your data, do you think that age is really a confounder, or could it be a mediator in that example that I just pulled up before? With hair dye, maternal age, and pediatric asthma. I think we already decided this a long time ago, but what's the consensus?
Well, it couldn't be a mediator because
Right.
hair dye use can't.
Right, exactly. So
Determine
we pretty much
duration.
exhausted this, right? So it's on the lab again, but I think we made it quite clear. So we're saying that maternal age could is probably a confounder based on last week's lab. And so what do you report? Question number 3 says, what do you report if it's a confounder with measure of association? Do you report if it's a confounder? The adjusted Mansell-Hansel, right? Good. And what do you report for a mediator? True odds ratio, risk ratio. Good. All right, so now let's do an analysis, finally. So now part 2, question 4, brings you into doing a stratified analysis. We did a stratified analysis in the lab last week, so you guys should watch that when we looked for confounder. Now we're talking a little bit about the possibility that we may have an effect modifier here. So the study is saying that we're looking at season of birth, as it may be a risk factor for asthma, with spring being the highest risk season due to the highest number of allergens that are in the air during the spring. And so you wonder if there might be an interaction between prenatal hair dye exposure and being born in the spring, such that the odds of asthma for those exposed to prenatal hair dye and who were born in the spring would most likely have asthma. So again, you can see that being born in the spring looks like it could be an effect modifier if you think about the definition. Because we're thinking technically that if you were born in the spring, when you were born, I should say, when you were born, could be an effect modifier. Because if you were born in the spring, we're thinking that if it is on that level, being born in the spring, you actually would see the association between hair dye and asthma. But if you're not born in the spring, so you have that other level of that third variable, then there would be no association, or less of an association, depending on whether it's partial or complete. So let's take a look at this. We want to determine whether being born in the spring is an effect modifier in between hair dye exposure and asthma. So what's the first thing we need to do when we do this type of analysis, determining for a confounding, remediation, or effect modifier, any of them. Find the crude, right. So we all know how to find the crude. Let's do that. Analyze descriptive statistics and then cross-test. Do I have one thing open? That is possible. Yes, it is. Thank you. So you guys do the crude. And if it's not the right thing, if I didn't post the right data set, you guys can find it. You could go to exercise 10, and that's the right. I think I did. So do the crude. Yeah, it should say exposure, asthma, season, and age. Those are the variables.
Which goes where?
So that's what I'm going to do with you.
Okay.
So tell me what goes where exactly. What goes where here? What's the main risk factor? Hair dye. So hair dye goes in the row. So that's exposure. Okay. Hair dye is exposure. But you know how I know? Look at your data and it says exposure, and you know that little label that I told you would be useful? It says prenatal hair dye. All right, so always look at the labels, because sometimes people will give you a database from another department and they'll do something like that. So exposure, hair dye is your row, in your row, because the exposure always goes in the row. And what's your disease or outcome? Asthma. So take asthma and put it in your column, because the outcome always goes in the column. Okay, and then go under cells, and then click on, under percentages, click on row and total like we've been doing all along. You don't really need to do that here, but let's just do it as a convention. And then go under statistics, and then click on risk. Then click on continue, and then click on paste. And then you get syntax, and then you can highlight it. Anybody stuck or everybody okay? Yep, I'll do it again. Analyze descriptive statistics, crosstabs. Okay, and then put your exposure in the row, put your disease, asthma in the column. Go under cells, and then under percentages in that little area here, click on row and total. Then click on continue. Then go to statistics, and then click on risk, which is under kappa. Then click on continue, and then click on paste, and then you should find it syntax. And then highlight the syntax, and then click on the green arrow on the top, and then run it. And you should get a crosstab, which we're all used to seeing. And underneath the crosstab is that nice odds ratio, risk ratio outcome. So what's the crude odds ratio in the relationship between hair dye use and asthma? Right, 6.05 right here. And remember that we also have to, we should report the confidence interval all the time. So 95% confidence interval is 2.1 to 17.3. Remember, this is odds ratio. The next one is risk ratio. It's not labeled, but this asks for odds ratio. So is this statistically significant, just for practice? Because I know we haven't done this together, so that's why I'm asking.
Yes.
Yes.
How many people say the 6.04 is statistically significant? Not everybody. Okay, that's good, I'm glad I'm asking. So we do have a couple minutes to review this. So I do stress that you should watch the hypothesis testing lecture really carefully, and then also listen to the lab audio, and that will really help you. So the confidence interval basically is the sort of random error around the odds ratio or the risk ratio, okay? So it basically means that the odds ratio that you are given here is the best estimate of what the odds ratio truly is. But the odds ratio could actually be as low as 2.1 and as high as 17.3. This is sort of like the range, but it's the random error around the odds ratio, okay? So, it could be as low as 2.1 or as high as 17.3. Now, for those of you who said that is statistically significant, because that's what this tells you. It tells you whether this odds ratio just happened by chance or it's statistically significant. So, some people said this is statistically significant. Why? Did you say that?
It doesn't include 1.
It doesn't include the null value of 1. This is a range. So the null value of 1 doesn't fall in between 2.1 and 17.2. It's over here somewhere, right? Just doesn't. So if the null value of 1 did fall in between it, what would that mean? Aside from the fact that it wouldn't be statistically significant, but why not? I'd rather explain to you why that's the case, this way you'll remember it.
Because there's a greater than 5% chance that you would have that null value.
As what?
If you did like 100
Right,
samples.
exactly. So you would have it as what, though? That the null value, which is 1, would be what? It could be what? The actual odds ratio,
Right.
which is what you meant, but.
Right.
So, in other words, if the null value of 1, and when I say null value, it's always 1. So if the null value of 1 falls in between the confidence interval, that means that the odds ratio or risk ratio could actually be 1. Because I said that this is really a random error around that. So the odds ratio could be as low as 2.1 or as high as 17.3. Yeah.
That kind of tripped me up when I was looking at the slide. So the null value, it's statistically significant if it has 1.
No, it's the opposite.
Oh, it's not significant.
Yeah, if 1 is in between these two values, then it's not statistically significant.
So if it was 3.3 to 17.3, and that's just it, there's no 1 in that.
Yeah, exactly. So that's another example where it's statistically significant.
So the 1 has definitely shown.
Yeah, so if I did something like 0.85 as my 95% confidence interval and 3.21, right, and it's a 95% confidence interval, right, and this is the way it's usually recorded. Okay, there's 1 fault in between both of these numbers on the number line, right? 0.85 to 3.21. See, there's a range. So on the number line, 1 is greater than 0.85, but it's less than 3. It falls in between those two numbers on the number line. You see that? So in this case, if that were to be the confidence interval and not this, it would not be statistically significant. Okay, trying to think of another. Yeah, so if it's like, I mean, it usually would be a decimal. So even something like this, having said that, say that this is my confidence interval. That's a comma. Is it statistically significant or not? And then the question in your head is, does 1 fall in between those two values?
No.
Right? The value of 1 falls after 0.99 on the number line. It doesn't fall in between these two numbers, so it is statistically significant. If 1 is included in this range, it's not statistically significant. Because that means that fair game, the way I had it before, say I do this. Can't really do that with this example. This means that the odds ratio, 6.0, is the best estimate for what the odds ratio is, but actually, it could be in between 0.85 and 8.99. The odds ratio could be 8.99, or it could be as low as 0.85. That's what it's telling you. It's like the random error around that. which means that 1, the number of 1 falls in between these two numbers on the number line, right? You know, 0.85 is lower than 1, but 8.99 is higher than 1. So that means that the odds ratio could actually be 1. Because the odds ratio could be any number between these two. Yes?
What's the point of it being a confidence interval that includes 1? Isn't it counterintuitive to do that?
Well, it's the statistical result that you're getting.
But if it's not statistically significant, what is it? Like, why have a 95% confidence interval, or why use that?
Well, the thing is, here's what you're doing. You're calculating this to determine whether or not it's statistically significant. That's what you're doing. You're running that test to see if it's statistically significant or not. So this helps you say if this is statistically significant. Okay, and then you report it to support your statement. So I would say the odds of getting asthma among those who use the hair dye is 6.05 times greater, right? But the result is not statistically significant in this case, using this, not this, but that, because the null value of 1 appears in a confidence interval. So I only use that just as a test to reach that determination. And that's it. Okay? So that's what the confidence interval tells you. Questions?
Now, doesn't it also say like you're 95% sure? that-
They don't want, some people in the department disagree with that statement and others accept it.
Yeah.
So I try not, that's why you don't hear me saying it, although it's still on the slides, because some people will say it's okay. But it's almost like what Bill said before about like if you try 100 times, you know what I mean? It's sort of like that. And that's really like on the slide, I think, too, right? That's what you saw it. Or did you just think of that or hear it from somewhere?
It's on the slide.
It's on the slide. So try to say it more like that. I won't mark you wrong if you say it that way. But that's really sort of the interpretation here. Now, aside from the 1, helping you determine whether it's statistically significant or not, the confidence interval can also tell you something else.
The size of the random error.
Yeah, exactly. How
Because
precise.
the wider the confidence interval,
Right, exactly. Right, exactly.
the
So
less accurate the
the
point is.
p-value, p equals, remember, if it's less than or equal to 0.05, it's statistically significant. If you ran both a p-value and a confidence interval, they would always jive with each other. So if your p-value is less than 0.05, that means it's statistically significant, so then the confidence interval wouldn't include 1. Although some authors report both, you don't really need to report both, but they would have to jive. This is either statistically significant or not, and you never find the p-value less than 0.05 with a confidence interval that includes 1. But the good thing about the confidence interval is the p-value only tells you whether or not it's statistically significant. The confidence interval actually tells you about precision in addition to the statistical significance. So you can look at the width of the confidence interval, as you saw in homework 2, and you can determine whether or not there's a lot of random error or a lot of variability around that best estimate odds ratio that you got. Because this is a best estimate. Even though it's there in your face, it doesn't mean it's exactly right. It's the best estimate that statistically that was calculated. So it's kind of hard. There's no real fast rule about this. This is kind of a decent amount of variability, because if I say someone's had 3 times the odds of getting the disease versus 8 times or 9 times the odds, there's a difference. So I would say that there's a good deal of variability around that. Now this is just an example, but the actual one we got, confidence interval we got, is 2.1 and 17. So again, it's statistically significant, because the null value of 1 doesn't fall in between the confidence interval. 1 falls before 2 on the number line. But also there is quite a bit of variability around that, because 2 times the odds of getting the disease versus 17, it's really not precise. The width of the confidence interval is wide. So there's a lot of random variability around the odds ratio. So the confidence interval tells you 2 things, and that's why we prefer to report them. Okay. All right. So getting back to this, shift gears back. Here's your crude odds ratio, it's 6.04. 0.05 to 1 to 10. All right, so you hold that on the side, and now for the, well, not really for the first time because I did it in the lab last week, you're going to do a stratum-specific ORs. So analyze descriptive statistics crosstabs. Where do I put the potential effect modifier here, which is age? Okay, no, I'm sorry, you're right. You're right. In the layer, good. So I take season of birth, which is my potential effect modifier, and I put it in the layer. This will stratify the results. This is what you would do if you were looking for confounding or mediation or effect modification. Remember when I had those two crosstabs side by side and I did age less than 65 and then age greater than age 65 when I did confounding for you in one of the first slides? This is how you will get two crosstabs side by side. Only SPSS does it one underneath the other instead of side by side. And then you'll also get two odds ratios. You'll get one odds ratio for the relationship between exposure to asthma and exposure to hair dye and asthma among those born in the spring. And then you'll get another odds ratio for the relationship between use of hair dye and asthma among those not born in the spring. And that's what we did on the slides. So you'll see it in a second. Everything else is set here, so if you go under cells, you still see under percentages, Rowan's modal is still checked, so that's okay. And under statistics, you'll still need the risk, which will also give you the odds ratio, so that's okay. So now let's click on paste, and then find your syntax, call it up, and now just get used to looking at your syntax. Here's hair dye by asthma. That would give you the crude, just like you did up there. But now I did it, to stratify it, I have a third variable by season. So that's what it looks like. So now you'll get those two crosstabs that you saw at the beginning of the lecture when I was doing confounding among the age groups. In this case, it's not among less than age 65 or greater than equal to age 65. It's about season of birth, being born in the spring and not being born in the spring. So run this thing, and if you look, instead of them being side by side, SPSS puts them one underneath each other. So here's a crosstab of asthma as the disease. Let me just do this like this. I'm just going to look at the top part first. That's why I'm bringing it all the way down, sorry, but I want to block out the other part. So this is the relationship between hair dye and asthma, just like we did before in the table, in the crosstab before. This is, I'm just looking at the first part of the table. So hair dye and asthma, but you'll see over here it says season of birth. So my total participants in this group is 38. What is 38? Who are those 38 people?
The people who are in the spring.
Exactly, right. Okay? So this crosstab only represents the relationship between hair dye use and asthma among those people born in the spring. So there's only 38 participants. Okay? If you look at the crude odds ratio up here, in total you have 75 participants. Okay? But there's 38 who were born in the spring. So that first part of the crosstab only does it stratifies by being born in the spring, and then if you scroll down to the second part of it, there's another crosstab here with asthma being in the columns, and hair dye, and then it's not born in the spring. So that's the second crosstab. Is everyone okay? And those people are 37 people not born in the spring. So 37 plus think it was 38 equals the total number of people in your group. Now if you scroll down again, you'll get your stratified ORs. You'll get an OR of the relationship between exposure to hair dye and asthma among those born in the spring and among those not born in the spring. So scroll down along that monster crosstab and you'll see this. So it's not just one odds ratio, now you have two, because it's stratified. So here we can just say that the crude odds ratio that we found a moment ago is 6.05. And the stratum-specific ORs are, for spring, it is 31.5, and for not spring, it is 1.95. 1.29. Thanks. All right, so those are my stratum-specific ORs, 31.5 and 1.29, and that's my crude OR. So remember, it's just like what we did in the lecture. Okay, just for practice, we don't really have to do this here, but this is an odds ratio for hair dye and asthma among those not born in the spring. That's the best estimate. This is the confidence interval around that, 0.2 to 6.8. Is this statistically significant or not?
No.
It's not, because 1 falls in between 0.2 and 6.8 on the number line. Is this, remember, it's going to give you two things. It's going to say statistically significant or not. Then the next thing is what? Is it precise or how wide it is? How much random error? So is there a lot of random error around this? That's estimate, yeah, because it could be as low as 0.2 times the odds or 6.8. Huge, a lot of random error. Is this odds ratio statistically significant? Yes, because 1 is not included there. And it's crazy wide, right? So it's like, so it's random, a lot of random error, a lot of variability around that estimate. Okay, but you know, we don't have to worry about the confidence intervals right now because we're still really focused on doing the steps.
So it doesn't matter if it's part of it isn't statistically.
Right now it doesn't. We're just doing it for practice, but I'm going to explain that in a second. Okay? Because you know, it's like you're looking at me saying, "But you told me I got never extend with them," and now you're saying it's okay. But for now, let's just do this, and then I'll talk about what we see. So, these are just steps that you learn. First do the crude, and then do the stratum-specific ORs. And that's exactly what I did, what we've done all along. So the first thing I told you to really look at is what? If the stratum-specific ORs are the same. Always do that, even for confounding and for mediation. Always look at the stratum-specific ORs. Get the crude, but then get the stratum-specific, and then first look at the stratum-specific ORs. Now, if this was confounding or mediation, these stratum-specific ORs would be very similar to each other, okay? And they would be different from the crude for confounding or mediation. But in this case, is that what we're seeing? I mean, really focus more, don't compare for that to that. If you see that these are different, I wouldn't even go and compare the stratum-specific to the odds, because you don't need to do that. So, are these similar to each other? Obviously not. These are very different from each other. 1.2 and 31.5, very different from each other. So, what do I think this might be? Effect modifier. It also, we said, meets the definition. We went through all of that. So this looks like it could be an effect modifier, but let's say it was 1.29 and 3.5. I don't know. Is that different or not? How do I know? Right? So the way to really truly know if these are statistically significantly different from each other is doing that Breslow Bay test and getting that p-value that I talked about in the lecture. Okay? So now we're going to do that to make sure that these are really different from each other. In fact, it kind of looks, I mean, it's kind of obvious, but we're going to see if they're really truly different from each other. So the way to do that is analyze descriptive statistics and crosstabs. And then go under statistics and do Cochrane and Mansell-Hansel statistics. Now, I know that we're not doing confounding, so you're not going to ever run a Mansell-Hansel adjusted summary OR unless, right here, statistics, and then Cochrane and Mansell-Hansel statistics. That's going to give you the Breslow day test. But don't get confused, because you really would only run the Mansell-Hansel if you thought it was confounding and mediation. So if the ORs were similar to each other but different from the crude, then remember I would get that weighted average, which is the Mansell-Hansel, so you would also check this off there in that case too. But this is where they put everything. So continue, and then paste, and then go to your syntax. And you'll see that it says you can still keep exposure by azimuth by season, and then over here it says CMH, so that's going to give you the Mansell-Hansel adjusted OR, which you don't need in this case, which is not confounding and mediation. And it's going to give you the Breslow day, which you need. So highlight this and run it. And now this is the first time that you guys are going to see the Breslow day. So here's the crosstab, the stratified crosstabs that we just saw. And then if you scroll below that, you still again see the stratified ORs just by spring. And then scroll down below that, and you see something called tests of homogeneity. This is the Breslow day test of homogeneity. Where's the p-value that I told you for doing this whole purpose? Where's the p-value? That's your p-value, 0.009. So crazy. So now we're saying that p equals 0.009. So the threshold to determine whether or not that's statistically significant is it less than p is less than 0.05. So is 0.009 less than 0.5 on the number line? Yes. So we say that, therefore, the stratified ORs that you see listed here, 31.5 and 1.2, are statistically significantly different from each other because the Breslow day p-value is less than 0.05. It's 0.009. So if the strato-specific ORs are statistically significantly different from each other based on this p-value, as you saw it was confirmed, then what do we have? Right, interaction or effect modification. I thought I said it wrong. Yes.
We only use that Breslow on the effect modifier?
Yes, exactly. Yep.
Can you say one more time? You said,
Sure.
therefore the stratified OR, blah, blah, are statistically significantly different from each other
Because the Breslow day p-value is less than 0.05. It's 0.009.
So it says, how do you interpret the strato-specific ORs? Is that a question you would ask? How would we, what
Yeah,
would be our
that's
answer?
going to come next, absolutely, and I'm going to tell you. And that's where that confidence interval question that was asked on this side of the room comes in. So I just want to make sure everybody's clear with that. I could go through that last part again with the p-value if you want. What's the consensus? Do a couple people need to hear it again? Yes? Okay, I got one yes, so I'm not going to. So what I did was I ran the p-value, analyzed descriptive statistics, crosstabs, and then under statistics I chose Cochrane and Mansell-Hansel statistics. That's how I'm going to get my Breslow day test p-value. I clicked on continue, then I clicked on paste, and then by doing that I got to my syntax and ran it, and then I got this output as a result of all of that. And you have to scroll down all the way below your odds, your stratified ORs. That next table is the Breslow day test. That's where you're going to get this p-value that's going to help you decide whether those stratified ORs are statistically significantly different from each other. They look really different, 31 point whatever it was, and 1 point whatever, or something like that. But we have to make sure they're statistically significantly different from each other. So this p-value right here which is in this output testing homogeneity, this is the Breslov-Day testing homogeneity, this p-value must be less than 0.05. If this p-value is less than 0.05, then that means that these two confidence intervals, not confidence intervals, these two ORs are statistically significantly different from each other. So in fact, that p-value is 0.009. So 0.09 is less than 0.05 on the number line. So therefore, because it's less than 0.05, we can say that these two ORs are statistically significantly different from each other. And if they are statistically significantly different from each other, it is likely that this season of birth is an effect modifier, or otherwise known as interaction term. Question?
When you have the two stratified results,
Yep.
if they're sort of similar to each other, you use that and the mental cancel to determine whether.
Yeah, so if these two, if we went to, let me know if this doesn't answer your question. Pretend we went through the thing and we have this third variable and we said it meets the definition of confounder.
Yeah.
That's the first part, all right? And then these two were similar to each other. These definition of confounder, and then the stratum-specific ORs are similar to each other, right? And were different from that crude.
Yeah.
Then you would run the Mantel-Hansel adjusted summary OR. Okay? And then the adjusted summary OR has to be different from the crude by 10%. And I'll say that rule, I'll send you that calculation. Once you do this and they're similar to each other for confounding or mediation, then you do the Mantel-Hansel, and then the Mantel-Hansel has to be 10% different from the crude. And then it's probably confounding or mediation, and your hypothesis based on whether or not it falls on the causal pathway will tell you whether or not it's confounding or mediation. Yes?
And with this, the effect modification one, if it's greater than 0.05, then it's just not.
It's not an effect modifier, and it doesn't mean you can then conclude that it's confounder. I mean, that just means that they're not statistically significantly different from each other, but if they don't meet the if the third variable doesn't meet the definition of confounder, and the numbers still look kind of different from each other, I wouldn't just go down the route of doing confounding. It could just be nothing.
Right.
Right? So it's hard. It's not, my suggestion is listen to the lab from last week, because it goes through the steps of the Mantel-Hansel, and I explain like how it has to be different from the crude, and when to do it and how it's necessary. So I do that like really slowly. Actually, this is all in one lab audio. I did it all together because it's sort of like a logical process of how to approach all three. So I didn't split it up. And that's posted under exercise 10 and also exercise 11. If that audio runs through the whole thing. Yeah.
I just noticed something that is really from last week about the Mantel-Hansel down below. It reports the estimate, and then it reports something called the IN or IN estimate.
That's the log of whatever, and you don't need to take the log, just
Okay.
take the value without the log. Take the OR without the
So
log.
it's just
and
one of
then
those things that might be
compensate
useful someday,
I know,
but you
yeah,
don't
it
need
is.
to worry about it
Exactly.
now.
Yeah, and some students wind up reporting the LN for the confidence intervals, those values, and the odds, but don't take the values that say LN before it. I don't know if it's here. You know what, I did that, listen to the audio, because I know I said that in the audio. And if I didn't, tell me, but I'm sure I said it about not taking the logs. So, always take, I'm trying to see if I can see an example of that output where it says LN. Here, yes, here it is. Yes. I knew it was here, I was dumbfounded that I couldn't find it. Okay, so This is the result of the Mantle-Hansel. This is effect modification.
Oh, it's
so we don't
ln,
need this.
not
Right,
I.
ln, yeah, it's ln.
For logarithm.
Yeah, exactly.
Oh, I thought it was in.
Pretend that we were doing confounding here, right? We weren't, we're doing effect modification, but just pretend we were doing confounding, and I ran this is the Mantle-Hansel. This thing is like weird. That's the Mantle-Hansel. This is the log estimate Mantle-Hansel, but we don't want that. That ln is bad. Don't take that, okay? And then this is the confidence interval around the adjusted OR. Okay? But then these are the log confidence intervals. See? So you don't want this. And you don't want this. But you want just the regular estimate and the regular confidence intervals, not the log. That's what you saw, Bill, right? Okay. So when you have confounded, like again, this what I just did here is not confounding, but I'm just showing you, and this is all of the audio for exercise 10 and 11, that if you have confounding, which is what we had in exercise 10, you would report the adjusted OR, which is the Mantle-Hansel summary OR. That's what you would report. And then you would report the confidence intervals. Okay? And just make sure that when you watch that audio, you understand how to report it, because you have to say after adjusting for that variable. So just watch that audio. I strongly recommend you watch that audio. So, all right, so now, what am I reporting in this case? We don't need the Mantle-Hansel here because we have effect measure modification. And sometimes you will hear people call effect modification effect measure modification. It's exactly the same thing, but different people use different things. So you heard me just slip, I just said that way. It's not wrong, it's just people's preference. So what am I reporting in this case? I have said that the Breslow-Day test has confirmed that these odds ratios are statistically significantly different from each other because the p-value is less than 0.05. So what do I report when I have effect measure modification? The strata-specific OR. So I would be reporting that odds ratio and this odds ratio along with the confidence intervals now, because now I'm reporting. So that's when the confidence intervals are important. They weren't helpful in determining it, but when you finally decide that you have to report it because it's effect measure modification, then you're going to report it. But there's something very interesting here. You see it? What's interesting about the confidence intervals here? And does it support what we're finding or the result?
For the not spring group, they're not statistically significant.
Right. But for the spring group, it is statistically significant. Does that further support effect measure modification? What is that showing you? And think about the definition of effect measure modification. What's the definition of effect measure modification? How would I describe it? Well, what's
different across groups?
Yeah, it's different across groups. So really, the association would only be apparent on one level of that third variable, right? So the relationship and the finding is really only apparent among those born in the spring. That's where the allergens are. But it's not apparent among those not born in the spring. That's why it's not statistically significant. So it further confirms it. It's interesting, yeah. Right? So.
Can you repeat that?
Yeah, sure, absolutely. All right. So here's the deal. With effect measure modification, the level of that third variable, and in this case it's being born in the spring or not being born in the spring, is the important thing. So the relationship between use of hair dye and asthma is only going to be present if it's on a certain level of that third variable. In this case, the relationship between hair dye and asthma is only present among those born in the spring. And it's not really present among those not born in the spring. And that's true effect measure modification definition. It's really the level when I say the level of the third variable, I just mean what the categories are, right? So the finding is really among only those born in the spring. That's where you see the association between hair dye and asthma. It's only among those born in the spring. It's not really among those not born in the spring because the confidence interval is statistically significant and you have an increased odds of getting asthma if you use hair dye and you're born in the spring. But here, if you're not born in the spring, it's not even statistically significant and the odds ratio is pretty low.
So, therefore, we can assume that there is no, that doesn't have a modifying effect or mediating?
It does. So I'm trying to think of a different way to say it so that everybody understands it. How many people understood the thing with the confidence intervals, what I just said, and whatever? Okay, so don't worry, I'm not going to let you say it out loud. I hate putting people on the spot. Let me try this again. Let me see if I can articulate it, because I know there might be just a couple of you who don't, because I didn't see all the hands go up. So with effect measure modification, the levels of that third variable will really make a difference in whether or not there's a relationship between the main risk factor and the disease. So only one level of that third variable will really have a finding, and the other level of the third variable won't have a finding. And that's how you know it's effect measure modification. Okay, because the finding will only be apparent in one category. Like with gender, it will only be apparent among men and not women. So in race, maybe among one race, not the other. So here, that third variable is called season of birth. And so the finding is only apparent among those being born in the spring. So there's a relationship between hair dye and asthma only among those born in the spring. And it's not among those not born in the spring. And the way we know that is because this finding is statistically significant. And that's among those born in the spring. This, based on these confidence intervals, is not statistically significant. And so that's showing you that these are among those not born in the spring. And that's supporting what we're saying, that the only finding is among this level of the variable and not among this one. I can tell you still don't get it, and that's okay.
So if the numbers were similar, then there would be no.
If they're similar, like if they're similar to each other, and the Breslow day test p-value is greater than 0.05, it's not effect measure modification. Okay? But here, these odds ratios are different from each other. And we know they're statistically significantly different from each other because the p-value is less than 0.05. But even further than that, so we know it's effect measure modification already, just based on that. But do you see that this is kind of the category where the finding is? And this isn't where the finding is? Because that odds ratio is so high. So what this is saying is that among those people born in the spring, people who use hair dye are 31 times as likely to get asthma compared to those not born in the spring. And it's statistically significant. Here, this is among those not born in the spring, there are 1.2 times the odds among those using hair dye to get asthma. And it's not statistically significant. So this isn't where the finding is. It's only among this level of the variable. Look at it a couple of times, and also listen to the audio because I say this again, and I may say it differently.
No, you're explaining it really
Okay.
well. My question is, when is it not obvious? Like,
So when is it? When are these?
when is it not obvious if there's a modifier or a confounding? Would the numbers be similar? Would the numbers?
Yeah. So this would not be a modifier. It's really based on this Breslow day. Okay. So if this Breslow day test, value is, it's up here now. If that's greater than 0.05, then I don't care what those odds ratios look like, even if they look different from each other, they're not statistically significant different from each other, so it's not effect measure modification. So nothing else matters in that point. It doesn't matter even about the confidence interval. That's why I didn't even want to do the confidence interval back then, because it would only confuse people. So I was like, look at the confidence intervals. Are they different from each other? Yes. They look visually different from each other. 1.2 and 31.5 are different from each other. Let's test it statistically and make sure they are statistically significantly different from each other. So this is the true test of whether they are truly different from each other. And that's going to tell you if it's less than 0.05, then it is statistically significantly different from each other. That these confidence intervals are different from each other. These odds ratios are different from each other. And therefore it's effect measure modification. And so what I'm saying even further than that is it confirms it by the confidence intervals. That the finding really is among only those born in the spring and not those not born in the spring. Any other questions about this? Well, it's exactly 850.
Wouldn't this also lead you to suspect that the real
It's being born in the spring and
exposure
not
is
hair
born
dye.
in the spring, not hair dye?
It's possible. But again, you have to look at the values and see if it's partial or complete based on the results. I don't think this is complete based on what I think the odds ratio would have to be if it was a total effect modifier. So, but it's possible. I mean, you could theorize that.
Could you run the tests the other way?
You can, yeah, look to see, absolutely, and see what you get. Yeah.
The next question says, can you definitely conclude that there is effect measure modification?
So what do you think?
Yeah. So I would say there's some evidence for it, but not.
Yeah, you know that.
Definitely.
Right. So, exactly. So you know by now that after all of this, you still can't definitively conclude anything. All right? So the way they would word this is that based on these results, it appears that being born in the spring is a significant effect modifier. It's a significant interaction term. They could say it both ways. But what might make you hesitate? What are some of the things you might be concerned about? I purposely did that. Yeah, the sample size. I mean, when you start stratifying on things, if you don't have enough participants, you get cells with 3 and 4 people in little, I mean, that's not really enough to really get a result that is meaningful. I mean, you usually don't get the confidence intervals that look like that with this. It's unusual. Sorry.
It's wise because you have a small sample.
Yeah, right, and that's why it's so wide. Exactly. That's why the confidence interval is so wide because the sample size is so small. That's exactly what you say. That's why. And so you would have to increase the sample size to reduce the random error so the width is right. So that's the hypothesis testing lecture. So that's the deal with this. And that's actually on this. The sample size is too small to produce precise stratum-specific estimates. Note the width of the confidence interval. Therefore, the investigator might want to use a larger sample in which to test its hypothesis. So, I will post this. It's posted, it's just hidden. So. Any other questions about this? No. Okay, so then we're back here again next Thursday. I don't know what topic next Thursday. Someone want to remind me? Is it infectious disease? Well, there is a lecture next week, but there is, yeah, but definitely, I think we're meeting, oh, it's not posted yet, but we are meeting. We're meeting in person next week. Make sure the scan's better, yeah. And they should be on top of each
That's true. And it's also good to stay for years.
I looked on the
You have a restaurant.
Yeah.
Oh.
Right. I mean, I didn't know.
If you're, I was gonna say, I can't remember an area that was.
was like,
Funny to see you
I
guys.
know, right? We're missing them for so long. Do you text me? No, right?
Bye. Did you get a new job?
Yeah, I did, one day.
Because I saw you on